Okay, we've had some practice with heat lost equals heat gain problems and one thing heating up another. This is one of those, but with a small wrinkle in that there's a special formula that we use when a calorimeter heats up instead of just a mass of water or a lump of iron or something like that. So we'll get to that in a moment. What we have here is a calorimeter, like the kind that you'd have in a chemistry lab, in which we've burned some heptane, and the heptane threw out some energy, and that energy heated up the calorimeter. And they want us to figure out what the specific heat of the calorimeter is. And they have a specific heat capacity just like any material does, except the units are a little different. We'll see how that works in a moment. The place where we can get started here, where we can start get some traction, is we have everything we need to find the energy from the heptane burn. The energy from a combustion equals N delta H. They've told us what the mass of the heptane is, which means we can get its number of moles, and they've told us its molar heat of combustion. So that's everything we need to get a total amount of energy. From there, we can turn around and figure out what happened to the calorimeter. We'll get there in a moment. So for now, the total energy equals a number of moles that we don't have. We're going to need the molar mass for heptane to do this. What's heptane anyway? You can look it up or Google it, or you can trust me if I tell you that heptane is C7H16. Which means its molar mass will be 7 times 12.01 plus 16 times 1.01, which gives us, what is that, 100.23? 100.23 grams per mole. Okay, if that's our molar mass, then the number of moles is mass divided by molar mass, which is 1 divided by 100.23 is 0.009977 053. We'll carry way too many digits for now just to make sure we don't get any rounding errors. So there's our number of moles. That's N. Goes right there. 0.009977053. And the delta H is given. It's 4816.7 kilojoules per mole. We multiply those out. And of course, there is a negative here that tells us the reaction is exothermic. We understand that, and I don't care about it for purposes of this formula. I just want to know how big the number is. At the moment, there's nothing that requires the fact that the reaction's exothermic. We just need total amount of energy. 48.05647, that's probably enough kilojoules. Because this was kilojoules per mole. This was kilojoules per mole. We multiplied by moles, so our answer comes out in kilojoules. That's the energy that was released when the heptane burned. Now, if we were heating up water or iron or any material like that, we would now write E equals mc delta T. This would be the amount of energy, and then we could solve for anything they wanted. But the special version that we use for calorimeters is a formula that just looks like this. If you're working with a calorimeter, calorimeters are designed to be an exact size and have standardized insulation and wall thickness and all that sort of thing. The designers know precisely what the masses of all of its components are going to be. And if you're following the directions, you're going to put a specific amount of water inside the calorimeter every single time, so they know that mass also. So what they do is they take care of this mass for you and they roll it up into the specific heat for the calorimeter. And instead of giving you masses and specific heats to calculate, they'll just tell you that this calorimeter has a specific heat of C. And they'll just give you this number. No mass is required. It's already baked into this amount. And you can tell when you've gotten one of these because when you get a normal specific heat capacity, its units will be joules per gram degrees Celsius. If you get a calorimeter specific heat, this kind, the units will just be joules per degree Celsius. And this makes sense. This formula has mass in it, and it has a unit that includes mass. This formula doesn't have anything to do with mass, and it's got a unit that also excludes the mass. So you can tell just from the units what kind of specific heat you've been given. And the temperature change is just like you're used to seeing for any other heating or cooling material. So this formula is simpler. It only works for a calorimeter and only if you've been given the right information, but it is a convenience and it saves you a little bit of work. And in this case, if we use the calorimeter formula, they're saying the total energy, well, we found that. It's 48.05647 kilojoules equals C is the specific heat. We're supposed to find that. We don't know what it is right now. And the temperature change is given as 13.2 degrees. So if we divide both sides by 13.2, we get that the specific heat for this calorimeter is 3.64. And this is kilojoules divided by degrees, so the C will come out in kilojoules per degree Celsius. And is that the right number of significant digits? I glanced up and saw this 3. I'm just making sure. Yeah, two of our numbers only had 3 significant digits, so this is an appropriate one for the answer. 3.64 kilojoules per degree Celsius.